Image anomaly detection refers to the identification of abnormality by only leveraging normal images in the training phase. Recently, anomaly detection has drawn lots of attention for medical image analysis because of its potential applications in medical domains. Intuitively, we can find the anomaly image by object detection methods based on deep convolutional neural networks. However, these methods usually depend on large-scale balanced data in the medical image domain, which is scarce and costly because of the concern for patients' privacy issues. Therefore, it is promising that only using normal images to train a model that can identify abnormal images. Typical anomaly detection methods are usually based on image reconstruction, which means given an image, an encoder-decoder structure reconstructs the input image. By minimizing the reconstruction error between the input image and the reconstructed image on the normal training data, the encoder and decoder get trained. To guarantee the fidelity of the reconstructed image on the normal training data, generative adversarial network-based solutions have been introduced into medical image analysis domain. However, all of them did not leverage any prior information, such as structures. Let's take the retina image as an example. In this case, the lesions of diabetic retinopathy destroy the blood vessel and histology layer in retina. Thus, in the abnormal retinal fundus image and optical coherence tomography image, the lesions broke the structure. The structure is the semantically meaningful edges in an image, which can help CNN networks make diagnoses to some extent. So how can we use the structure? From all the above, we propose PNet, which leverages the dependencies between structure and image texture for image and structure reconstruction circularly, and use reconstruction error for both structure and image as normality measurement. The overall pipeline is straightforward. Firstly, the structure extraction network GS is trained for extracting structure S from the original image I, and then the extracted S and the feature encoded from I are fused for reconstruction. Finally, we further utilize the reconstructed image I hat to extract the S hat and measure the difference between S and S hat. Our PNet encodes the relation between image texture and structure by enforcing the consistency of the image and structure between original and reconstructed ones. Using the Retinal Edema Segmentation Challenge dataset, and a fundus multi-disease diagnosis dataset to evaluate, we found that both datasets lack structure information. To avoid manually annotating the structure, we try to train a network for structure using existing datasets that have vessel segmentation in fundus images and layer segmentation in OCT images. Besides, as different datasets have different noises and data distribution, we leverage ADA-Seg, a domain adaptation-based image segmentation method to learn the structure extractor GS. The training loss in this module is shown here. Since the structure is represented by vessels in fundus or layer section in OCT, and the ambiguity exists for the direct mapping from structure to the original image, we propose to introduce texture information as complementary information of the structure, and the texture which provides the details over the local regions. Specifically, we encode the original image and its structure with EN1 and EN2, respectively. Then we concatenate the two features and feed them into a decoder to reconstruct the original image. The training loss in this module is shown here, where D is the discriminator. We further append the structure extractor GS to the reconstructed image to enforce the structure extracted from the original image and that from the reconstructed image to be the same. Also, as some lesions are more discriminative in structure, there is significant difference between extracted structures from the original image and reconstructed image which can be used for normality measurement. The loss function in this module is simple. Then, we arrive at the objective function of our PNet, where lambda1, lambda2, and lambda-s are the hyperparameters. Finally, we combine image reconstruction error with structure difference for anomaly score measurement, and a higher anomaly score indicates that the image is more likely to be abnormal. We use the Retinal Edema Segmentation Challenge dataset and fundus multi-disease diagnosis dataset to train our network. Here is our result compared with other baseline methods on both datasets. We show the qualitative effect of multiple cycles in the test phase. The abnormal lesion becomes more and more similar to normal patterns, which is a little like anomalies repairing. Such a phenomenon is more obvious in the structure map. For the healthy image, both the image and structure map remain the same even after multiple cycles. We also apply our method to the MVTech AD dataset, which is a very challenging and comprehensive anomaly detection dataset for general object and texture images. That's anomaly detection in the medical domain, structure, and PNet. Hope you enjoy this video.